Hello everyone, welcome back to Avinash Explains Tech YouTube channel and our Microservice Masterclass. In part 1 we learned what asynchronous communication means, how message brokers works and how Kafka differs from RabbitMQ. We discussed producers, consumers, topics, partitions, exchanges, queues and consumer group. But publishing and consuming message is only the beginning. Imagine that the order service publishes an order created event. The payment service receives it, deducts the payment, but crashes before confirming that the message was processed. Now we have several important questions. Should the broker deliver the message again? If it is delivered again, could the consumer be charged twice? How many times should a failed message be tried? What happens to a message that can never be processed? Next question is, how do we preserve the order of related events? These are the real production challenges of asynchronous communication. In part 2, we will cover message acknowledgements, retries, and dead letter queues, delivery guarantees, message ordering, idempotent consumers, common mistakes, and production best practices. So let's begin with the message acknowledgements. When a broker delivers a message to a consumer, it needs to know whether that message was processed successfully or not. This confirmation is called an acknowledgement, commonly known as an ACK. Let's understand it with an example. Suppose RabbitMQ delivers an order created message to the inventory service. The inventory service must read the message, validate the order, reserve the inventory, save the result in its database, and send the acknowledgement. The message should only be acknowledged after that important business processing has completed successfully. What is successful processing? If the inventory service successfully resolves the product, it can send the acknowledgement. RabbitMQ can then remove the message from that queue. The flow will become like message received, validate the message, reserve the inventory, and save in database and acknowledge and send the acknowledgement. This is the successfully processing message pattern. Next is processing failure. Now imagine that the inventory service receives the message, but its database is temporarily unavailable. The consumer cannot complete the operation. Depending on configuration and failure type, it may reject the message, send an negative acknowledgement or NACK. Ask the broker to requeue it, route it towards a retry mechanism, send it to a dead letter queue. A NACK communicates that processing was unsuccessful. However, the requeuing every failed message immediately can create a serious problem. Suppose a message contains invalid data. The consumer receives it, fails it, requeues it, and immediately receives it again. The cycle continues. Receive, fail, requeue, again receive, fail, again requeue. This is called poison message loop. It consumes resource without making any progress. That is why acknowledgements must work together with the bounded retries and dead letter queues. Okay, now let's see the Kafka and acknowledgements. Kafka uses different model. Kafka uses different model. Kafka records are not normally deleted when consumers reads them. Kafka records are not normally deleted when a consumer reads them. Instead, each record has an offset, and consumer track their progress by committing offset. Imagine partition contains these offsets like 100, 101, 102, 103, 104. If the consumer successfully process record 103 and commits its progress, Kafka knows where that consumer group should continue. This creates an important design decision. Should the consumer commit the offset before or after processing? Should consumer commit the offset before or after processing? So this is the question. Let's understand what is commit before processing. Suppose consumer commit the offset first and then begins the processing. If the application crashes during processing, Kafka may consider that record completed. When the consumer restarts, it continue from a later offset. This message may effectively be lost from the application point of view. Okay. The next is commit after processing. Now suppose consumer process the message first and commits the offset afterwards. It processing succeeds, but application crashes before committing. So Kafka may deliver the same record again after restart. This can cause duplicate processing. In most business systems, processing a message more than once is safer than silently losing it. However, this means consumer must be idempotent. We will discuss idempotency shortly. Now let's see retries and dead letter queue. Not every failure should permanently stop message processing. Not every failure should permanently stop message processing. Many failures are temporary. For example, the database temporarily unavailable, the downstream API times out, the network connection is interrupted, the service is restarting, the rate limit has been reached. If we try the operation again after some time, it may succeed. That is why messaging system need a retry strategy. Immediate retries, the simplest options is to retry immediately. For example, attempt 1 failed, attempt 2 failed, attempt 3 successful. Immediate retries may work for very short transient failures. However, they should be limited. If the database is unavailable for 5 minutes, retrying 1,000 times within a second does not help. It only increases system pressure. Right. Next is delay retries. The first one was the immediate retries. The next one is the delay retry. The better approach is to wait for a next attempt. For example, attempt 1 wait for 5 seconds, attempt 2 wait for 30 seconds, attempt 3 wait for 2 minutes. This is called backoff. With exponential backoff, the delay increases after each failure. We can also add a small random delay called jitter. Jitter prevents thousands of consumers from retrying at exactly the same moment. At exactly the same moment when dependency became available again and again. Now let's see the retry queues. In RabbitMQ, a common design uses separate retry queues. The flow might be main queue, consumer, failure, retry queue, after delay, main queue. The message waits inside the retry queue for configured period. After that delay, it is routed back to the main queue. The message should carry retry information such as number of previous attempts. When the maximum retry count is reached, it should no longer return to the main queue. Instead, it should move to the dead letter queue. Now let's see next is Kafka retry topics. Kafka applications commonly independent a similar pattern using retry topics. For example, order events, retry 1, order events retry 2, order events DLQ. A failed message may first move to the short delay retry topic. If it fails again, it can move to the another retry topic with longer delay. And after the maximum number of attempts, it moves to the dead letter queue. The exact implementation depend on the application and framework. Now let's see what is dead letter queue. A dead letter queue, or maybe it is called DLQ, stores message that could not be processed successfully after that allowed retries. For example, a message may reach the DLQ because the message format is invalid, the mandatory field is missing, the reference customer does not exist, the schema is incompatible, business validation repeatedly fails, a dependency remains unavailable beyond the retry limit, the consumer contains a bug. A DLQ prevents one problematic message from blocking the complete message flow, but creating a DLQ is not enough. Someone must monitor it. If thousands of messages remain inside the DLQ and nobody investigates them, the system is still losing business operation, just more quietly. For each DLQ messages, we should preserve useful information such as original payload, original topic or queue, error message, stack trace reference, retry count, failure timestamps, correlation ID, consumer name, and application version. After correcting the pattern, after correcting the problem, the team may replay the message from DLQ, but replay must be controlled. Before replaying, verify part of original operation already succeeded. Otherwise, replay could create duplicate business actions. Okay. Now let's see the next topic is delivery guarantees. Messaging systems generally discuss three delivery guarantees: at most once, at least once, and exactly once. These terms describe how many times a message may be delivered or processed. At most once, at most once means that a message is delivered 0 or 1 time. There is no retries. This gives us a lowest delivery overhead, but a message may be lost if a failure occurs. Imagine a consumer marks a message as completed before it finishes processing. If it crashes afterwards, the message may not be delivered again. At most once can be acceptable for non-critical information. For example, some telemetry data, non-critical metrics, typing indicators in the chat application, temporary location update, data we are losing an occasional update in acceptable. Data we are losing an occasional update is acceptable. It is not good choice for payment or financial transactions. Next is at least once. At least once means the system tries to ensure that the message is delivered. However, the same message may be delivered more than once. Suppose the payment service completes a transaction but the acknowledgement or offset commit fails. The broker does not know that processing succeeded, so it delivers the message again. Now the consumer receives a duplicate. At least once is common because it avoids silent message loss. But the consumer must be able to handle duplicates safely. Most common systems combine at least once delivery with idempotent consumers. Exactly once sounds ideal. This means the business effect of a message should happen exactly one time, but the achieving true end-to-end exactly once processing is difficult. Kafka provides exactly once feature within a specific Kafka workflow using idempotent procedures and transactions. The next point is message ordering and partition. Many business workflow depends Many business workflow depend on event being processed in the correct order. Suppose an order guarantees these events: order created, payment completed, order shipped, order delivered. What happens if order delivered is processed before order shipped? The state of system becomes incorrect. Ordering in Kafka guarantees ordering within a single partition. It does not guarantee ordering across all partition of a topic. Suppose order event topic has 3 partition. If all events for the same order use order ID as a key, Kafka send them to the same partition. For example, key order ORD 5001 partition 0, ORD 5002 partition 2, ORD 5003 partition 1. All events for ORD 5001 remain in partition 0 and can be processed in order. Different orders can be processed in parallel across different partitions. This gives us both ordering and scalability. The selection of message key is therefore an important architecture decision. If we use a random key, related event may go to the different partitions and ordering can be lost. If we use the same key for every message, all messages go to one partition, preserving global order but destroying parallelism. The key should usually represent the business entity whose event must remain ordered, such as order ID, customer ID, account ID, patient ID, and device ID. Ordering during retries. Even when message enters the same partition in order, retries can affect business processing order. Suppose message 101 fails, but the consumer continue processing message 102 and 103. Now later message may complete before the failed message. For some use cases this is acceptable, but for the other use cases processing must stop for that key and partition until the failed message is resolved. This creates a trade-off between strict ordering and throughput. Now let's see the ordering in the RabbitMQ. RabbitMQ generally delivers message in order, but several conditions can affect the final processing order. For example, multiple competing consumers, message redelivery, different processing times, consumer failures, priority queues, and retry queue. Suppose consumer A receives message 1 and takes 10 seconds to process it. Suppose consumer A receives message 1 and takes 10 seconds to process it. Consumer B receives message 2 and complete it in 1 second. The messages were delivered in order, but their their business processing completed out of order. If strict ordering is required, we may need a single consumer for that queue. Separate queues based on entities key, controlled concurrency, application level sequence checks. Again, strict ordering usually reduces parallel processing. We should require it only where the business genuinely needs it. The next point is idempotent consumers. We have already discussed multiple times, but we'll discuss. An idempotent consumer can process the same message multiple times without producing an incorrect additional effect. Let's understand with this an example. Suppose a payment service receives the command to process the payment of 2500. The first time it received the message, it charged 2500. If the same message arrives again, it must not charge another 2500. The final result should remain the same as if the message had been processed only once. Okay, the next point is message ID tracking. One common strategy is to give every message a unique identifier. The consumer maintain a record of processed message ID. The flow becomes receive message, check message ID, already processed, yes, ignore. If no, then process message and save the message ID. If that message ID arrives again, the consumer finds it processed message, stores and safely ignores the duplicate. The second point is transactional processing. The business update and processed message record should ideally be stored in the same database transaction. For example, begin insert into processed message ID. Values where message 9001. Update the payment status captured where ID is 5001 and commit. The unique constant on message ID prevent the same message for being inserted twice. If the duplicate arrive, the unique constant detects it. However, the both action must belong to one transaction. If we update the payment but crash before saving the message ID, the duplicate may be processed again. The next is natural idempotency. Some operations are naturally idempotent. For example, set status to shipped. Running this operation twice may produce the same final value. But an operation like increase reward points by 100, this is not naturally idempotent. For non-idempotent operation, use a unique event or transaction ID. External system. Idempotency became more difficult when calling an external IP. For example, external API. For example, when calling a payment providers, include an idempotency key if the provider supports it. The payment provider can then recognize that two requests represent the same business operation. Without this support, retries after an uncertain response can be risky. There are some common mistakes like no idempotency, infinite retries without backoff, ignoring poison messages, assuming global ordering, creating too many Kafka partitions, sending very large messages, no monitoring, treating event like database tables, publishing database changes unreliably. So there are some Best practices and key takeaways: use schema versioning, include useful metadata, monitor the complete messaging flow, use bounded retries, monitor and message DLQ, make consumers idempotent, secure the broker, choose the correct tool, and let's summarize the part 2. Acknowledgement tells broker or consumer system that message has been processed. Retry help recover from temporary failure, but they must be limited and delayed. DLQ isolate message that cannot be processed successfully. At most once delivery may lose messages. At least once delivery may create duplicates. Exactly once business processing require cooperation between broker and application design. Ordering is generally guaranteed only within a control boundary such as Kafka partition. Idempotent consumers make duplicate delivery safe, and production messaging require proper schema, monitoring and security retries and operational process. The most important lesson is asynchronous communication does not remove failure. It gives us a better way to isolate, absorb and recover from them. That is the complete episode 12 and our two-part discussion of asynchronous communication using Kafka and RabbitMQ. If you haven't watched the first part yet, watch it to understand message broker architecture and the fundamental difference between Kafka and RabbitMQ. In the next episode, we will explore event-driven architecture. We will learn how event connect multiple microservices, how event-driven systems differ from a simple messaging queue, and how patterns such as transactional outbox help us to publish events reliably. If this video helped you, please like it, share it, and subscribe to Avinash Explains Tech YouTube channel. Also answer this question in the comments: how do you prevent duplicate message processing in your application? Thank you for watching. Keep learning, keep building, and I will see you in the next episode. Thank you so much.